Archimedes is the crown gold. When a crown of mass 14.7 kilogram is submerged in water, an accurate scale reads only 13.4 kilogram. Is the crown made of gold? So if the crown is gold and its density and specific gravity must be very high, that should be about 19.3. We determine the specific gravity using the Archimedes principle and the two free body diagrams. So apparent height, so apparent weight is expressed with the combination of actual weight and buoyant force. That should be W, actual weight, minus buoyant force at B. So that should be net weight, apparent weight appearing in the actual weight. So W prime minus W minus the actual weight minus apparent weight is the buoyant force. So now this actual weight is mass times gravitational constant G. So this one should be M G, which is rho naught times volume V times G. That is mass. So basically, if you plug that into this formula, then the buoyant force also function of the density of the fluid or and the volume. So that should be rho F V Z. So that buoyant force is the effective force, artificial force applying to an object which is actually replacing the amount of environmental liquid. So if you plug that, then the equation should be omega minus, W over W minus W prime, the ratio of the weight between the actual and apparent weight is basically rho V Z over rho F V Z. Here, V Z and they all cancel out from the numerator and denominators, only leaves rho naught and the rho F. The ratio between the density ratio between the two different material. So now if you compare that the weights of these two measured values, that it will provide the density of the material too. So now as you see that the rho over rho F, the ratio of density between the two different material is ratio between actual weight and the apparent weight. Now you plug the numbers, and that is actual weight is 14.7 kilogram. So you just plug the number into the W, and the apparent weight is 13.4 kilogram. So that provide the ratio between these two density. So from that, the crown, this crown is not made out of the gold because, well, that's ratio of density is so much different. So it's clearly just showing that the crown is not made out of the gold, out of this ratio.
Okay. Okay. Okay, got it. All right. I can change it. Oh. All right. Okay, got it. Okay. So basically, if you compare that two weights, that net weight is equivalent to the buoyant force. So if there's no, the difference, then that buoyant force should be the equal to zero. So that's make a, that lead to the direction of two weight are in the same values. So if you compare that, then that provide the density between the two different, material, which is the density of the gold and the environmental fluid. So depending on the ratio that giving you the how much that difference between the apparent weight and the actual weight. Okay, so that's the first example problems we start with today. Any question regarding the first one?
No.
That let's move on to the next one. Okay, let me open this example problem, and I'll get you another few minutes. So, in order to help you, let me just read it. Floating buoyance and density. In figure 14-11, which is one in your right, block of the density 800 kilogram per cubic meter float face down in the fluid of the density 1200 kilogram per cubic meter. The block has the 6 centimeter height. So number one, by what depths H is the block submerged, and B, if the block is held fully submerged and then released, then what is the magnitude of its acceleration? So you can take a look at the figure on your right, and then use that to solve this A and B. Do you need help?
Yeah.
Okay, so in order to solve this problem, you have to just consider two different, maybe like one basic conditions. So as you probably know, the floating need the upward buoyant force. Like if the density of the submerged object has less density than the one fluid in the environment, then that produce the positive buoyant force, which is upward, right? So that upward force on the block should be same as downward gravitational force on the block too. So the buoyant force basically is equal to the weight of the fluid displaced by the submerged portion of the block. So with that idea, you can maybe drive the formula based on the definition of the buoyant. So let me show you that video based on that the idea. You can maybe just take a look. So that is this one.
Sample problems 14.04. Floating buoyance and the density. In figure 14-11, a block of the density low 800 kilogram per cubic meter floats face down in the fluid of density low F 1200 kilogram per cubic meter. Block has the height H 6 centimeter. First question, by what depth H is the block submerged? Number B, if the block is held fully submerged and then released, what is magnitude of its acceleration? So let's take a look at the first case. The buoyant force is same as gravitational force applied to the fluid, which is replaced by that block. So number A, buoyant force is the effective force or effective mass in case that the amount of the volume is replaced by the box. The amount of volume of the box is replaced by the fluid. So here the MF is the mass of the fluid displaced by the submerged the portion. So number one, the fluid floating requires that the upward buoyant force on the block match the downward gravitational force on the block. So if the buoyant force now is upward and gravitational force downward, so if these two forces are equivalent and they are balanced, then that make this object, this block, actually floats inside of this submerged on this fluid. And buoyant force is equal to the weight mfg of the fluid displaced by the submerged portion of the block. So that should be rho equals mass over v, that is density, and the mass should be therefore the density of fluid times volume of fluid. So from that, F buoyant force mf times g should be rho f, the volume g, actually volume f times the g. So here, this volume f is the block's phase length. So here, that should be L times W. Here, L is the length, the phase length of the block. And this is width. That's short. So this is like a volume. So if you place it, then that should be rho f L W. Oh, here's actually h. There should be h too. H, the height, times g. So similarly, gravitational force Fg is m times g. Here m is rho, and that should be volume V, and that should be also the g. So that rho, the V volume is L W H. That's volume of the object, the block. So if you replace the V with that, then rho, that should be rho L W H, the G. So floating block is stationary. That means the upward force and downward force, they're stay in balance. So if you apply the Newton's second law along the y-axis vertical direction, then that force should be equal to 0, because they're not moving downward or moving upward, or there's no up and down movement. So that indicating that the force from gravitation and the buoyant force is stay in balance. From that, F net y vertical direction is y. That should equal 0. So if you plug that the two forces into this Newton's second law, then that is F buoyant force minus gravity Fg should be m times ay, and ay equals 0. So that is m times 0 should be equal to 0. So from that, if you plug buoyant force and the gravitational force into this formula, then that should be rho F L W H G minus rho L W capital H G should be equal to 0. From that, you can find the relationship between the the height of box and the submerged portion of the box in this liquid, the water. So from this one, that LH just cancel out of first and second terms, and G also too. So the H submerged part of this box in this you know the fluid is measure between these two different material, the fluid and the box, times height of the box. So that the density of the box is 800 kilogram per cubic meter, and the density of fluid is 1200 kilogram per cubic meter, and height of this box is what, 6 centimeter, right? So from that, the height of submerged portion of this box in equilibrium of the movement should be 4 centimeter. And now let's take a look at the acceleration. How much acceleration so number B, the block is held fully submerged, then released. What is magnitude of acceleration? You just press this box complete submerged into this fluid, and you just let go of the box. Then the box will just push it back against the buoyant force. So that start to have some sort of acceleration from the rest. So we gotta just.
Tatiana, do you understand the second circumstance, the second condition? What's happening? I want to just make sure you understand the second question.
Yeah, like yeah, like they put the box fully underwater, and then when they let go, the buoyant.
So basically, the buoyant force is bigger than the gravitational force. So the buoyant force push the box upward, and then they start to have like some sort of oscillation motion, like back and forth, until that box, reach the equilibrium between the gravitation and the buoyant force. I want just to stop the video though, because I want to make sure you understand this second question though. Okay, I'm gonna continue this video.
Just to find out the magnitude of its acceleration from that condition.
Oops. I think. Why is that stuff? Oh, okay. Let me then finish. I don't. Maybe that's kind of cut. So basically, hold on. So the number B.
Yeah.
Okay. The B. Oops. Hold on. Okay. There. Okay. So the B is now you have the total volume is L, length of the box, and the width and the height, the total volume. So now you have buoyant force upwards. That's more than the the gravitational force. The box is no longer stationary. It is no longer stationary. So that has the upward motion. So if take the gravity out of this buoyant force, then that produces net force upward, which is actually mass times acceleration upward. So now if you plug this the buoyant force expression and the gravity into this formula, then that should be rho F, the density of fluid times L H W H Z from here to here is actually mass of the fluid minus minus the low L W H Z. So this is the mass of the box, and that it should have low L W H A, that box mass still. So that create the Newton's based on that create the equation based on the Newton's law. So if you rearrange this formula in terms of acceleration A, you can find the relationship. So A is if you move that LH could be LWH could be out of this formula, right? They're all same. So they're existing everywhere. So we can take this out of it. Then that's acceleration itself is just the ratio between the density between the fluid and the box minus 1 times gravitational acceleration G. Okay, that's easily simplified. Now you plug the density numbers out of the fluid and the box. Then it's 1200 kilogram per cubic meter divided by 800 kilogram per cubic meter minus 1 times gravitational constant acceleration constant value is 9.8 times 9.8 meter per second square. Then that lead to the answer is 4.9 meter per second square. So if you fully submerge this box into this fluid and then just take off your hands, then when this box coming out of the water, that comes with 4.9 meter per second squared acceleration. And once it's actually reached the equilibrium and there's no longer, downward force. So, but there's some kind of spring effect. Once you actually this buoyant force push that box and that's going up, and at some point gravitational force becomes larger than buoyant force and then just drag that box downwards. But just like a simple harmonic oscillation, that box will have some sort of like oscillation motion, but that size of oscillation amplitude of oscillation becomes smaller and smaller as time goes, just like spring. So that's fluid play a role as a spring in this dynamics. Okay, but that's the first concept, condition of the box in motion is based on that breaking the balance between the buoyant force and gravitational force. Okay. Do you have any question?
Not right now.
Okay. Let's just move on to the next one then. Okay. So example 13-15, flow and pressure in a hot water heating system. Water circulate throughout a house in a hot water heating system. If the water is pumped at a speed of 0.5 meter per second through a 4 centimeter diameter pipe in the basement on the pressure of 3 atm atmospheric pressure, what will be the flow speed and the pressure in 2.6 centimeter diameter pipe on the second floor 5 meter above? Assume the pipe do not divide into the branches. So the one pipe goes all the way through this heating system. So there's no change of the pressure into the sub branches of the pipe. Okay. So the equation you can use is actually Bernoulli's equation. So let me write it down for you. So that is pressure 1 is pressure 2 is same as pressure 1 equals low density times gravitational acceleration constant times difference of the height between the two spots and plus the kinetic energy change of the kinetic energy between two spots. So that is Bernoulli equation. You can maybe just use to solve this problem. I will get you a couple of minutes to solve this. So that's just the description of this problem sounds like really complicating, but all you need is plug the numbers into this formula. I mean, Bernoulli equations. So basically, that all the parameters, the pressure and the height of two different spots and the speed of the water, they're all provided in this problem. So you need to plug them into this formula. So do you want to watch that video?
Yeah.
Okay, let's show you. I'll show you that. That is, I think, this the one.
Flow and the pressure in a hot water heating system. Water circulates throughout the house in a hot water heating system. If the water is pumped at a speed of 0.5 meter per second through the 0.4 centimeter diameter pipe in the basement under pressure of 3 atm, what will be the flow rate and the pressure in the 2.6 centimeter diameter pipe on the second floor 5 meter above? Also, the pipe do not divide into branches. Okay, so we have to use the Bernoulli's equation to solve this problem. So there are two spots have the different pressure and density, the pressure and the speed flow conditions. So we gotta apply that to solve two variables out of two equations. So let's take a look at first condition. You gotta figure out the some given parameters out of the given conditions. So let's take a look at the first the velocity at the that the 2.6 centimeter diameter pipe on the second floor at 5 meter above. So the velocity V2 is the so basically if you the amount of the fluid passing through the two different spots in given time should be same. So basically you have the amount of the velocity of fluid moving through the certain position of this pipe should be so basically what I'm trying to show you, the total amount of the fluid passing through the given time should be always same regardless of their spot. So if you have two spots in the pipe, and that's amount of that volume should be delta M1, should be delta M2, and this amount of the mass through this portion of the pipe within time T1, then the ratio, the mass flow of this, the fluid passed through this pipe in given time T1, the ratio should be same for the different spot, maybe second spot or so, anywhere in this pipe actually should be there's the volume, I mean, the quantity should be exactly the same. So if you replace it, this one, if the fluid move the distance L, dl over delta T time delta T1, and if fluid moves delta T2 over time T2, then that the volume should be low times V1, which is low times delta L, and the cross area of A1. And when that fluid pass through the second spot of this pipe, and obviously the size should be different from 1, and that should be low V2 equal, that is the low delta L2 area 2. So because of this fluid assumed to be the incompressible, that density must not be changed, so the load that should be same. So this amount of mass rate in given unit time must be conserved at different spot of the pipe, as long as the fluid pass through with the same ratio. So this delta M1 over delta T1 should be same as delta M2 over delta T2. That indicating that the ratio of the mass flow in given time must be same regardless of their spot the fluid path through. So if you plug that number, that should be low delta L1 A1 over delta T1 should be same as the low delta T L2 A times A2 to be the cross section is A1 and the cross section is A2, then that should be delta T2. So now, as I said, this fluid is incompressible, so the density is the same, it's just conserved. And from that, delta L1 over delta T1 is obviously the velocity 1, and delta L2 over delta T2 is velocity 2 at second spot. So basically, velocity, average velocity times area should be conserved. Value from that, in this condition, the 2.6 centimeter diameter pipe at second floor 5 meter above, the velocity should be expressed by the velocity at 4 centimeter diameter pipe by the basements and their velocity and area. So that is that should be B1 times A1 over A2, or B1 times A1 over A2. So this area is a function of the radius of R of the pipe. This one 2 pi R2 squared. So the R1 here is half of the diameter, so 4 centimeter over 2 is 2 centimeter. And R2 is half of the diameter at 0.2, second point, so that should be 2.6 over 2, so that is 1.3 centimeter. And then B1 is 0.5 meter per second. If we plug the numbers into this formula, then that should be 0.5 meter per second times 0.02 meter square over 0.013 meter square. So that leads to the answer of velocity, which is 1.2 meter per second. Now, we gotta plug this velocity into the Bernoulli's equation to find out pressure at second floor 5 meter above from the basement. So based on according to the Bernoulli's equation, pressure is relative pressure is the reference pressure plus density times G times difference between the two different points in vertical orientation plus their kinetic energy difference. Okay, so now we gotta plug the numbers into this formula to estimate the pressure at the spot of our interest, which is 5 meter above the basement. That is, now we know the pressure at basement is the 3 ATM, so that is 3 times 10 to 5 Newton per square meter plus then low is 1.0 times 10 to the 3 kilogram per cubic meter times 9.8 meter per square second times the height difference is y is y 1 minus y 2 is the 5 meter above, right? So that is minus 5 5 meter. Okay, then plus 102 1.0 times 10 to the 3 kilogram cubic meter times 0.5 meter per second square minus 1.2 meter per second and square. So you plug that numbers, then it will lead to the answer of 2.5 times 10 to the 5 Newton per square meter, which is same as 2.5 ATM. So if you fluid the hot water into the 4 centimeter diameter pipe with a 0.5 meter per second at the basement, and you measure pressure, the initial of that pressure at that basement is 3 atm. But when you just take that water out of the pipe of 2.6 centimeter diameter and second floor, the 5 meter above the reference spot, then that pressure is cut down to the 2.5 atm from 3 atm.
Okay, you got it?
Mm-hmm.
Does it make sense, right? Okay. So, do you have any question?
Not right now.
Okay. Then hold on a second. Let me check. Maybe we can finish the last two, sample problems in the next week. But I think right now, because your school has not even started like this, fluid topic yet. That's what you said, right?
Yeah.
So, do you have any exam schedule, test schedule coming up soon regarding the angular moment and the rotational motion topic?
We have one the week after this break.
Week after, okay, so you still have time. So do you have any handout, the worksheets distributed by your teacher?
Oh yeah.
So maybe it's better to work on that next session. If you send me the copy of that, I'll take a look at it, and maybe we can discuss together in the next session. How about that?
Okay.
In order to prepare your exam.
Okay.
Because you have plenty of time to get into the fluid topic. So it's better to spend time for preparing your next exam. So just email me if you have any copy. Email me as soon as possible. I'll take a look, and maybe you can walk through that next session then.
Okay.
Okay. Any question? Anything to discuss? Okay. I'll see you next Monday, right?
Yeah.
Okay, I'll see you the next Monday then. Okay. All right.
Okay.
See you then. Bye.
Bye.